Last lecture of today, I will talk about graph sketching. And upon thinking, okay, I will get to the problem of finding wires in the walls of houses, but I can't help covering connectivity through graph sketching because it's very cute and simple. Okay, so we will talk about the graph streaming model of computation, so I quickly defined that for you. Edges of a graph G arrive in an arbitrary order in a stream, just like that. The vertices are known to us. They're numbers 1 through n. Here they are shown in green. The algorithm gets a single pass over the stream. And at this point, edges are just inserted into the stream. And as the algorithm is scanning the stream, we wanted to use only n polylog n bits of storage. So that's the space requirement. Good. These are known as insertion-only streams. Edges are only inserted into the graph. Here's a very simple problem, most basic problem that I want to consider in this setting, which is construct a spanning tree of the graph, well, assuming it's connected in a single pass. Okay, it is extremely easy in insertion-only streams. All right, we're just looking for spanning trees. Edges keep coming, and if we store a forest at every point in time. If the new edge coming in closes a cycle, we throw it away. If it doesn't, we add it to our forest. That's n log n space and solves the problem. Good. So let's see how this works. This red is my forest. Say the black edge comes in, and I don't take it. I close the cycle. Okay. Wonderful. So in insertion-only streams, the spanning tree problem is very easy. Fantastic. Now, how about streams where edges get to arrive and depart, namely dynamic streams, so streams with edge deletions? Now, here, the situation seems to be significantly harder. Well, for example, look at this graph. It could be that we're observing a stream of edge insertions and deletions, and at some point during this stream, the graph looks like this. Look at this red edge. This red edge is crossing a cut, so this edge is somehow critical to the connectivity of the graph. Okay, so whatever the algorithm is storing at this point in the stream should be very correlated with the presence of this red edge. The algorithm should know about this edge at this point. Great. Now we are in insertion deletion in dynamic streams, so let me just add a few more edges to the graph. I'll add a bunch of edges that go across the same cut. Fantastic. So here's the second snapshot of the graph in the stream. Now this cut is this particular edge. This edge was red. This edge is not particularly important. And for that matter, I could have added a complete graph at this point. Okay, so let's think about it. So what does the algorithm store at this point? It seems like what the algorithm stores at this point is not really correlated with this edge that used to be red. The edge is unimportant. Aha, but we are in the dynamic streaming setting, so at the next stage, I could just go and delete all the edges that I added, and I'm back in this situation. And this edge here is important again. So what could we possibly store so that we know about the presence of this edge exactly when it is important, despite the fact that throughout the stream, the importance may go up and down? All right. So clearly, very different algorithms are needed, and that's exactly where sketching comes into play. Right? There's really, at this point, only one generic hammer that we have to handle dynamic streaming problems, and that's make the algorithm maintain a linear function of the stream. Good. So how do we apply sketching techniques to graphs? What exactly do we sketch? So here's a very beautiful idea introduced by Anguch and McGregor in SODA 2012, and in the same conference independently by Valerie and Bruce Capron. The idea is to apply sketching techniques to the edge-vertex incidence matrix of the graph G. All right, so this is the matrix that featured prominently in Sushant's lectures. Here it is, the matrix B. It has n choose 2 rows and n columns. The columns correspond to vertices. The rows correspond to edges, or rather potential edges. I wanted to have a fixed dimension. A row is 0 for pairs of vertices that are not an edge in the graph. And if an edge UV is in the graph, then the row is non-zero. There is exactly one 1 and exactly one -1. 1 at U, -1 at V. Choose the orientation of this edge any way you like. It does not matter. All right. Excellent. Good. So as stated, rows are indexed by potential edges or pairs of vertices, and if the edges in the graph, then the corresponding row is the difference between the indicator of one of the vertices and the indicator of the other vertex. Great. So rows correspond to edges.
So the screenshot shows the same notation.
Yes, exactly.
Same convention.
Yeah. You seem to be in the other one.
No, I'm a fan of this one.
All right. So what is the key property of the edge vertex incidence matrix that we're going to use? The key property is the following. Oh, there's a typo that's supposed to be a C. So suppose that I'm interested in a cut C in the graph. I'm interested in the set of edges crossing from C to the complement of C. Good. Let X be the indicator vector of one side of the cut, C. There's a vector of length n that has ones on vertices that are in C and zeros elsewhere. Good. Key claim that we're going to use is that B, the edge incidence matrix times X, is the indicator of the cut. Well, it's a vector of length n choose 2. I claim that it has non-zeros exactly in edges that are in the graph and cross the cut. The non-zeros might be a 1 or a +1, but I don't really care which one it is. Good. Proof. The proof of this claim is by picture, and this is the picture. All right. Suppose that I'm interested in this cut that we considered before. So the corresponding indicator vector is X. It is ones on these 4 vertices and zeros on the others. Excellent. Now let's consider B times X. B times X is basically the act of adding up the columns of B corresponding to vertices in X. So if I consider an edge, if I consider an edge UV such that both endpoints are in C, then the 1 and the -1 cancel because I add up over all the vertices in C. If the edge has both endpoints not in C, I also get a 0. And if one endpoint is in C and the other is not, I get a 1 or a -1. There's no cancellation. Excellent. Good. So how do we use this observation to solve connectivity in dynamic streams? So that's the result of Anguche and McGregor. Great. Let's start with a very natural and simple algorithm for connectivity, for constructing connected components. And then we'll verify that one can implement it from a sketch. So here's our graph. The algorithm will proceed over a logarithmic number of rounds. And the algorithm will maintain connected components in the graph. We'll merge them together as we go along. So we start with our collection of connected components, calligraphic C0, as containing the singleton vertices. Okay, so here they are, the green vertices. Then in every round, we look at all the connected components in our current collection, and we choose one outgoing edge. Every component chooses one outgoing edge. In round 1, every vertex chose a neighbor. So this is shown with red arrows. Right, and note that it could be that one vertex chose the other, and this vertex chose the other one back, or more interesting things can happen. So, good. So we do this, and then we just merge the corresponding connected components and add a spanning forest on the selected edges. Right, so the set of selected edges could have cycles, but we prune this. So after the first round, we have a connected component of size 2 here, another connected component, and a connected component of size 4. Excellent. We just simply do this again. In the next round, every connected component chooses one outgoing edge. Say this connected component, these 2 vertices chose an edge here, the red arrow. This connected component chose this edge, this chose this. Again, merge the corresponding connected components and add a spanning forest on the selected edges. Good. Now we're done in 2 rounds in this particular example. Of course, it is not hard to verify that the number of connected components at least halves in every such round. So in order log n rounds, we will be done. Good. Now I claim that we will be able to implement this algorithm given a sketch of the edge-vertex incidence matrix of our graph. Why? This is because for each, this main operation in this algorithm is the following operation. We have a set of vertices in the graph, C, and our task is to choose one edge going from C to the complement of C. Now, by the key property that we proved by picture just a few moments ago, choosing an edge from the cut induced by C is the same as choosing one non-zero element of the from the vector B times the indicator of C. Okay? And I claim that this can actually be done using a linear sketch, a pre-computed linear sketch of B. These sketches are called L0 samplers, and I will quickly tell you on the board what these are. And I will not tell you how to construct them in the interest of time. It's a very nice exercise. So what is an L0 sampler? An L0 sampler is a sketch S. It's a random matrix with m rows, and in this application, n choose 2 columns, such that for any given x in R n choose 2, one can recover one element of support of x from S times x. Okay? I'm simplifying the definition a little bit. If you look up the proper definition of L0 samplers, you'll realize that they return a uniformly random element of x. These details are not very important for this application, so I'll simply skip them. Okay, so it's a sketch that returns one element of the support of x. And how many rows does this sketch have? The number of rows depends on the success probability of the sketch, but very importantly, it's polylogarithmic number of rows if the failure probability is inverse polynomial. Again, the fine details of this are not very important. Good. So such sketches exist and can be constructed without too much effort. And in fact, we already know tight bounds on the sketching complexity of this L0 sampling problem. So equipped with these sketches, here's how we can solve dynamic connectivity. Look at our algorithm that proceeds over order log n rounds, and note that at every step in this algorithm, we need to choose one edge going across a certain cut. So what do? We simply pre-compute capital T, plus 1 L0 sampling sketches, and maintain sketches S of the edge-vertex incidence matrix B, S0B through STB. These matrices, S0B through STB, are very small. The number of rows in this matrix is polylogarithmic. That's the number of rows in the sketch. The number of columns is n. Right, so let me just draw this here, perhaps. Okay, so the edge incidence matrix was n choose 2 by n. We're sketching it down. We're sketching the large dimension down to the polylog number of rows. So as we go through the stream, the algorithm is maintaining n polylog n bits of information. So every vertex maintains a small polylogarithmic size sketch of its neighborhood. Great. So then, once in the algorithm, we need to select a edge going across a cut C. What do? We simply run the decoder of the L0 sampler on ST times B times the indicator of C. Now this might look very simple, but this is where the magic is happening in fact. So somehow the challenge here, the apparent challenge is that we do not really know which cuts will occur in the decoding process before we see the graph. Nevertheless, we were able to pre-compute a sketch from which we can decode the edge that crosses the cut. So what we're really interested in is one element, one edge crossing the cut C. As we know, this is one non-zero of B times 1C. So we would like to have an L0 sampler of B times 1C, but by linearity, this is the same as the L0 sampler of B times 1C. So despite the fact that the algorithm is very adaptive, and we don't know which cuts we will have to use when we decode, we're able to pre-compute sketches that let us support any execution path of the algorithm. Okay. Yes?
And you can use the same sketch for all the cuts produced at the same level of proof.
Excellent question. So Anupam is asking, is it true that you can use the same sketch for all the cuts at the same level of this process? The answer is yes. There are no dependencies there. This is very, very nice. Good. So as mentioned, a similar result was obtained by Valerie and co-authors.
Sorry. It's 13.
13. Oh, apologies.
Okay.
How come this?
I
I'm
think
pretty sure this is 12.
mine is 13. Theirs is 12.
Oh.
And I didn't even know about theirs. And mine wasn't a sketching result. It used full memory. It used
Right, but the techniques are the same.
the techniques look the same. I didn't think of it the same way at all.
I see. Sure, yeah. This seems very cool. yours uses XOR, right?
Yeah, I used XOR and I used it based on parity.
So I have two questions about this. Are these two results equivalent? And we have to do this computation, right? This looks like it's linear in the size of C, which will not
great.
be so
Yes.
good.
So wait. The first question was, are these results equivalent? I didn't fully understand it. What do you mean?
Yes, Valerie's result and the sketching result.
They're not equivalent, but they basically discover this beautiful idea of sketching. Valerie doesn't call it sketching, but that's what she does.
Okay, sorry.
It wasn't sketching for me. I wasn't trying to save memory. For me, it was just understanding that sampling would reveal the names of the edges because of parity, the parity of the sums of the degrees. That, so it's different. And of course, mine was about the time needed to come up with to get the answer, and theirs was about the space needed.
Yes. So maybe I was. They're the same thing from a very high level, right? The main idea, the beauty here is the fact that you can do cancellations, right? And that's the key idea. The rest is bells and whistles, and this idea is. All right, I should stop. Okay, it's a beautiful idea. That's what I want. That's what I had. All right, and now your other question was?
The time to compute that is proportional to C or something.
Oh, no, yes, the time to compute this is indeed C, but that's great, right? Basically, we look at S times B, that's a matrix with n columns and polylogarithmic number of rows, and at every round in this process, we have some partition of the vertex set. Now, for every partition, we just go and add up the columns corresponding to vertices. For every element in the partition, we go and add up the corresponding columns of S times B.
That's linear in the size of C.
No, it's just fine.
The overall runtime will not be competitive with algorithms that are not streaming algorithms. I think that's
No, the overall runtime is also n polylog n, right? Because you.
Okay. From a sketching point of view, they weren't concerned. They weren't asking that question.
Yeah.
My algorithm was.
Oh, for the good.
Was use data structures to do it fast.
Right, exactly. So this is not about dynamic algorithms that maintain the solution fast. When I said bells and whistles, that's not what I meant.
So let me just very quickly add some bells and whistles for Bob, and since I know both communities quite well. So I mean, in the one sketching community, they're happy with order n time. No problem, right? And what we do in the data structures community is that we, for example, have an Euler tour of each component. We just sum up these things.
I know the solution.
Wait, okay. But that was just the translation.
But the point is, the sketching community, linear time to the end,
That's great.
okay, which is not the case
No.
in the data structures.
Right.
But Valerie's solution uses polylog bits, so it's the same space efficiency.
Exactly.
She wasn't shooting.
Yeah, so in the sketching community, we don't, these results don't care about maintaining an actual solution at all times efficiently, which was the focus of Valerie's paper. But no, I have excellent open problems related to exactly that. I think it should be possible to merge the two, merge this. All right, good. So as Anupam was asking, at every level, we do get to use the same sketch, but note that we do need a separate sketch per level because of adaptivity. That's exactly these issues that our guarantees what we run the sketch on should be independent of the randomness of the sketch. Okay.
Valerie ran into exactly the same problem in her solution.
Yes. Good. Also for this, for the dynamic connectivity problem, or at least for the distributed version of this, we currently have tight bounds. So if you tighten up the parameters in the solution of Anguch and McGregor that I presented, you get n log cubed n bits of space. And this is optimal in some senses.
So I don't have a solution that uses n log to the 3. Oh, sorry. We use that many bits. Sorry, never mind. But the time isn't, yeah.
Right.
Time isn't.
Good. Okay, so let me skip the lower bound discussion in the interest of space, because I would like to talk about the spectral sparsification question, because it is very cool. So in the remaining time, I'll try to give some of the main ideas behind our algorithm. So this is a paper with Aaron and others that gives a sketching linear space sketching algorithm for spectrally sparsifying graphs, and also provides linear time decoding at the end of the stream. All right, so since Sushant discussed spectral sparsification, I'll go fast here. So there's not much to be carefully explained. So we're given a graph G, n vertices and edges. We want to find a spectral sparsifier G prime. So I'll explain what it is. Good. So maybe we all know what spectral sparsification is. So good. So as Sushant proved in his lectures, one way of obtaining spectral sparsifiers of graphs is through importance sampling. This is the result of Spielman and Srivastava. What one does is for every edge in the input graph G, one computes the effective resistance of this edge in the electrical network that G is. If you think of every edge as a unit resistor. So this is denoted by RUV. And then samples these edges with probabilities proportional to the resistances. What is proportional to the resistances? It's something of the form, you take the resistance multiplied by a large constant times log n by epsilon and cap this at 1. So if this is more than 1, you make it 1, you have to take that edge. Good. And if an edge is sampled, then it's assigned probability 1 over PE. With high probability, as Sushant proved, we get a spectral approximation to the graph G. So the Laplacian L prime of the resulting sparse subgraph sandwiches the Laplacian of L in the positive semi-definite order. Good. Good. So now, again, suppose that the graph is given to us as a stream of edge updates. Now, if we're dealing with insertion-only streams, this is not a very difficult problem. It's a nice exercise, how to sparsify graphs in polylogon space and insertion-only streams. Intuitively, it makes sense, because if some edge, you maintain some subgraph of the input graph, and for example, you could morally take the next incoming edge and measure its importance with respect to what you currently have. If the importance is not high, then you might want to drop the edge. And since edges only come in the stream, this is insertion only, if something was unimportant, it'll only be less important because you're adding edges and resistances go down. Okay, so again, what I would like to understand is what to do if you have edge deletions. And that's a completely different question for a similar reason. Edges can be important, then they look unimportant, and then they're important again. We will use linear sketching, and we will use the techniques that we designed in lecture 1, namely the count sketch primitive. As you remember, the original applications are to data streams. So we'll take our edge vertex incidence of the graph. Here it is, matrix B. It has n choose 2 rows and n columns, just like in our application to connectivity. And we will left multiply it with some carefully designed sketch. Fantastic. So then the space complexity of our solution will be the number of rows in the sketch times the number of vertices in the graph. So we'll maintain a small matrix. Every vertex maintains a polylogarithmic sized summary of its own neighborhood. Right? So recall that basically for a vertex, the column of the corresponding column of the edge vertex incident matrix encodes the neighborhood of the vertex. So vertices sketch their neighborhoods independently. Good. And the question that we want to resolve is, how do we design a small sketch from which a spectral sparsifier of the graph can be reconstructed, and reconstructed quickly? All right. So let's first figure out how we would do it if we didn't care about the reconstruction time. I just want a small sketch from which a spectral sparsifier can be reconstructed quickly. So somehow I'm supposed to, well, I will implement effective resistance sampling. But there's a challenge because I don't know the graph, so I don't really know the effective resistances. And I need to sample with probabilities proportional to those. Okay, let's look at the simplest possible setting. Recall that we sample edges with probabilities proportional to effective resistance, and the constants of proportionality is some kind of a log n factor. So edges whose resistances are large, say larger than 1 over log n, they need to be with probability 1 added to the sparsifier. Okay, so let's understand how to solve a simpler problem. I want to design some kind of a sketch such that from this sketch, I'm able to recover the high effective resistance edges in a graph. I don't care about the rest. It will be fine later. Good. So this is our goal. Design some sort of a sketch S with a polylogarithmic number of rows from which we can recover the high effective resistance edges of G. Okay. Now this problem by itself actually is a little too hard. So I'll give myself more of a hint. The hint will be the following. Besides the sketch of the graph that I want to approximate spectrally, I'll assume that I'm also given explicitly a crude spectral sparsifier of G. What is crude? A factor 10. So I'm given explicitly a small n polylog n number of edges graph whose Laplacian L spectrally approximates my Laplacian up to a factor 10. Don't ask me where I get it from. I'll tell you later. Good. And now this problem already has a nice solution, so let me tell you what the solution is. Good. We need to find the high effective resistance edges. So let's recall from Sushant's lecture what that actually means. What does it mean for an edge to have high effective resistance? Well, the resistance between a pair vertices U and V is the following object. What is this? It's the voltage difference across U and V that is induced by the experiment of injecting 1 unit of current at U and taking it out at V. This is exactly what this formula computes. L inverse times BUV gives us the vertex potentials, the voltages on the vertices that will result in flow with demands BUV. Demand BUV, remember, is just -1 at U and +1 at V. That's exactly the experiment of taking out 1 unit at V and injecting it at U. Right, so that's these are the voltages, and this BUV transpose just measures the difference across U. Okay, fine, that's what resistances are. fantastic. Here's a picture that goes along with this. Let's say here's an edge of pretty high effective resistance, and here are some voltages. Okay. I was sending a unit of current from here to here. Good. Now, if phi is a vector of vertex potentials, then the flow, the electrical flow induced by these potentials is just the differences. The flow on an edge xy is just the difference of phi y and phi x. Good to know. So basically, the edge vertex incidence matrix, right multiplied by the vector of vertex potentials, is the flow vector. Good. Now, this gives us, in fact, another characterization of effective resistance. The effective resistance of an edge UV is the fraction of L2 squared norm, or the energy of electrical flow, unit electrical flow from U to V, that sits on this edge. Okay. So if the resistance of an edge is large, 1 over log n, this means that this edge contributes a non-negligible fraction of the energy, dissipates a non-negligible fraction of the heat that is dissipated by the entire flow network if you inject one current at U and take it out at V.
You're assuming unit rates.
Yes, everything is unit rates. Good. Very nice. So given this, this we don't know currently, don't know at this point how to use, but this is a good characterization of effective resistance for us. Here's how we will use it. Let's design a test primitive. So remember, I was telling you that you're standing in front of the wall in your house, and you get to hook up the batteries and send flow from one point to the other. We're designing this experiment now. You're given a sketch of the graph G and the crude sparsifier, and now you have a pair U and V, and you want to know whether UV is an edge of high effective resistance. If it's an edge of low effective resistance, you don't care. You only need to know if it's a high effective resistance edge. Here's the ideal thing that you want to do. It is exactly the experiment that I described. You go and hook up the battery, and you send the unit of current. And then you check if the edge heats up sufficiently well. Okay, how do you check this? Well, you sort of might want to form the flow vector F by taking the edge incidence matrix, right multiplying it by the vertex potentials. Maybe this is the vector. And let's say right now I'm testing this edge, so it contributes a lot of heat. It's a high effective resistance edge. You have a large number there. Right. Now, it's a nice experiment, but of course you can't do this in streaming because you don't know the graph, you can't form the flow vector. Good. But, oh, yes, and if the edge is a non-edge, then you get a 0. But note that we don't have we don't need to answer very fine-grained questions about this vector. It's a very long vector, but all that we need is to know whether a given coordinate in this vector contributes a 1 over log n fraction of the total energy. As we will see in a moment, this is exactly what you can do with count sketch. So that's what we did in lecture 1. So this will be solved with count sketch. Good, we'll do this in a second. There is another problem here. The other problem is that, as stated in the experiment, I say, oh, I will compute the correct vertex potentials, so I send the right flow. Of course, I don't really know the graph the graph G, so I can't compute the right vertex potentials. Remember, I assumed that I also have a crude spectral sparsifier of my graph as a hint. I'll send the flow there and use the same potentials, and this will work. It is fine. It's not necessarily a flow then, but it's fine. Good. So to summarize, what we want to do is to run this experiment of hooking up a battery. Ideally, we would like to, if we knew the graph, we would form the flow vector and test if the pair UV contributes a large fraction of L2 squared norm. Can't do this, but in order to be able to figure out if a given coordinate contributes a large fraction of L2 squared norm, you don't need to know the entire vector. It's enough to know a sketch, and specifically a count sketch. So this question with parameter eta is solved by a count sketch. All that we need to do is hash into something polylogarithmic number of buckets and do our repetitions. I will not do this very precisely here. As long as we hash the flow vector of length n choose 2 into a polylogarithmic number of buckets, we will be able to get approximations to individual entries that are more precise than 1 over polylog n fraction of the total L2 squared norm. And that means that we'll be able to know if a given edge is a high effective resistance edge in the graph.
So this is just for one edge, no?
This is just for one edge. Yes.
And
Please continue.
so you want to do it in, so you'll do it in, for every edge you'll do this.
Yes. So right now we're doing a very slow solution. We'll try every pair. Every pair you view. Basically, right now I don't care about runtime. I just want to convince myself that I can at least have a small sketch of the graph that I can then decode. So let me define the sketch, and then we'll see if this generates a question. Basically, this is my algorithm for this problem at the moment. I will take a sketch S, which is the count sketch with some polylogarithmic number of buckets. And my algorithm is going to maintain, as the edges come in, S times B, the edge incidence matrix of my graph. Okay? So what is this? This is a matrix of roughly this shape, a polylogarithmic number of rows and n columns. So now I look at this matrix, I have my crude sparsifier, and you give me a pair of vertices and you say, okay, tell me if this pair UV is an edge of high effective resistance in the graph. What do? I take my crude sparsifier, I route a flow from U to V there. This gives me some vertex of potentials phi. Then I take this matrix that I have and I multiply it by phi. I can do this here. This one is better. Okay, so I'm storing S times B, which is a matrix like this. This is sort of polylog by n, right? So then, given U and V, I compute some vector of potentials. These are the potentials that induce a unit UV flow in some graph that is similar to mine. And then I look at S times B times phi. And then what will happen is that this is, again, by this magic of linear algebra, is S times B times phi.
So you do it offline.
Right? Yeah, I'll do this offline at decoding stage. All right. Now, this object here is what? This object here is actually the flow vector. So I have a sketch of the flow vector, and then I go and check if corresponding coordinate is large. Cool. All right. Any other questions? Thank you. This is great. So, fantastic. So basically, every vertex computes such a sketch, and here's the same equations on the slide. All right. So now we have UV. We compute the potentials phi. Okay. And then we, by magic of linear algebra, by associativity, get access to the sketch of B times phi.
Sorry, we're probably missing something. How did you? We have not yet checked that this is an edge in the original graph.
Okay, you're saying we haven't checked that this is an edge in the original graph?
Like in the stream.
Right. No, we don't know that.
We don't know that.
We're trying to check, and we can't know if this was an edge. Maybe this was a low effective resistance edge. I just don't have enough information.
I understand, but you could find a pair that has high effective resistance, but was not an edge.
Yes,
in the graph today.
Such a pair definitely exist, but then if you form the corresponding flow vector, right, in the actual graph G, and look at how much energy the entry UV, entry corresponding to that pair contributes,
I see.
You'll see a small number. It'll be 0 actually. Right. The edge is not there, so there'll actually be 0. You will not know that it's 0 because you don't know the entire flow vector, but you have a count sketch, and the count sketch tells you that whatever it is, it's much smaller than a 1 over polylog fraction of the total energy.
Thank you.
You could also do the k-sparse covering to see if it's in the list, right?
I don't think so. Nothing is sparse here, right?
Oh, just the K heavy hitters. It has to be a.
Yes, exactly, exactly.
Sorry, no. So just do K
Yeah.
heavy hitters, and it has to be one of them. So
Yes,
right?
you can do that. Right, exactly. So you can either think of count sketch as just approximating the values, that's good enough, or you can think of we didn't really cover algorithms for how to generate the list of heavy hitters fast. You can do that. That's also perfect. Good. So that's what we do. Wonderful. And well, this is great. So this, as of now, we designed this test. We know that the act of hooking up a battery to two junction points on the wall of your house, this corresponds to testing whether the energy of some electrical flow is mostly contributed by the pair UV. Good. And this already gives us a low space sketch that you can decode in quadratic time. Of course, there are details. We've only explained how to find the heavy resistance edges, but it's okay. All right, so now let's design a fast decoding algorithm. So I have this sketch of size n polylog n, but if you ask me to decode it, I'll start trying all pairs of vertices. That's not nice. Let's do a linear number of tests.
So before you do that,
Yes.
you haven't told us how to get rid of the assumption of no. That's recursion, you're saying?
I didn't tell you. Maybe now is a good time. All right, so how do you get rid of, Chandra's question was, how do you get rid of the assumption that you have a large constant factor approximation to your graph? I don't want to tell you about this because I only have 15 minutes and I want to cover the fast algorithm. I'll tell you later. Okay. Good.
Exercise.
Yeah, it's an exercise. That's a hard one. All right. Good. So we have this method. Hook up the battery to the endpoints. Great. And yeah, so you see, if an edge is high effective resistance, like this edge is high effective resistance, then it lights up. It contributes a lot of heat. If you hook up a battery to an edge that is low effective resistance, it doesn't light up. All the flow goes many ways, and the amount of heat contributed by this particular edge is low, it's a small fraction. Good. So then, yeah, so this is my interpretation with finding wiring in a house. So let me show you this picture at least. Yeah, the circuit is from XKCD. The dots are from me. There are actually more than 70 dots in this picture. I think I got to 50 and then it was hard to stop. Yeah. Anyway, so this is the situation, right? So you have the vertices and then you can attach a battery and then feel the very hot edges. Great. So let's see how to do this. So suppose that there is an edge UV that is a high effective resistance edge, and we need to find it. So far, we only know that it will light up if we hook up the battery to U and V. To save on the number of tests, we need to find a different characterization of edges of high effective resistance. We would like to find another pair AB in V, another pair of vertices, such that UV will light up. It will carry a lot of energy, carry a good fraction of AB flow. Send flow from A to B, and UV suddenly shows up. Right. If we manage to do that, then we have a shot. It will be. Formally, what does this mean? And so I'll give you the full proof, because this proof is very, very short and clean. So let me try to go slowly and really be formal. What does it mean for UV to carry a lot of AB flow so that we can detect it? Well, let tau be the vertex potentials induced by the corresponding AB flow. L inverse times BAB, as Sushant was explaining. Then the amount of flow on the edge UV is just the difference of potentials. So the energy is the difference of potentials squared. And then our Count's cage primitive only detects edges that are large in relative terms. So we care about the total, the contribution of this edge relative to the total energy of the flow. The total energy of the AB flow is actually the effective resistance from A to B. That's another fact. Good. So that's the condition that we need. We need to find a pair AB such that the potential difference squared across UV divided by resistance of between A and B is still roughly 1 over log n. Good. What is 1 over log n? Really what we mean is that it should be roughly the ratio, roughly the fraction of energy that UV contributes in its own electrical flow. And that fraction is what? Is phi u minus phi v. Phi are the UV potentials divided by resistance of UV. Good. Yes, let's skip these examples. To find such a pair AB, we will use something that some of us may have learned in high school in electrical networks classes. And this is known as the Reciprocity Theorem. The Reciprocity Theorem says that the potential difference induced on a pair AB by sending a unit of current from U to V is the same as the potential difference induced on UV when you send a unit of current from A to B. So you can reverse the experiment. It's all the same. Mathematically, this is just the symmetry of a certain expression that we'll see. Okay, so suppose we send the UV flow. UV flow results in potentials phi. That's L pseudo inverse times BUV. Good. AB flow results in potentials tau. That's L pseudo inverse times BAB. Then the potential difference across UV in the AB experiment is BUV transpose tau. So that's BUV transpose L inverse BAB. The potential difference on A across AB induced by the UV flow is just the transpose of that. It's BAB times phi. So you just transpose this expression to transpose a number, it's the same thing. So that's the proof of the reciprocity theorem. Thanks. All right, so why is this useful? Why is this useful? So we're trying to find this pair AB that will carry a good, such that UV carries a good fraction of AB flow. So let's look at the UV experiment. And phi are the potentials in the UV experiment. When you send a unit of flow from U to V, the minimum potential will be at U, the maximum at V, and everybody else will be in the middle. So here's the picture that goes along with this. All the other vertices are somehow in the middle. This is U, this is V, and these are all the other vertices of the graph. So we call this the potential embedding of U and V. That's an embedding of the vertices of the graph induced by sending a unit of flow from U to V. Okay, good. So let's look at this expression again. So phi U minus phi V is sort of large, right? We start with the assumption that UV is a high effective resistance edge, so the potential difference between phi U and phi V is large. If we look at this potential embedding, well, we realize that for any vertex x, phi U minus phi V, here's x is in black, can be written as phi V minus phi x, and then plus phi x minus phi V. We can split the potential difference as from U to x, and then from x to V. Excellent. Now, what we're going to do is we're going to take X to be a vertex that is not too close. Sorry. For every vertex, take X and look at the one of the vertices, U and V, will be kind of far from X. X can't be close to both. So the potential difference from X to one of the endpoints will be at least a half of the potential difference from U to V. And so the experiment that we will be running is the experiment of sending flow from X to the endpoint that is far enough from X. That's what we will apply the reciprocity theorem. So let me just do this carefully. So consider the experiment of sending flow from X, this middle vertex, really think that it's in the middle, to U. Let tau be the corresponding potential. What's the potential difference across U and V in this XU experiment? Well, by the reciprocity theorem, it's the same as the potential difference from U to X in the UV experiment. Right. But we know that the potential difference from U to X in the UV experiment is large. X is in the middle. Or rather, we can choose U to be the further of the two pairs from X. So this is excellent. We already found an experiment, X to U, for which the potential difference on UV is comparable, at least a quarter, of the potential difference across UV in UV's own experiment. Wonderful. All right, so it seems like we're done. And really, all that we did is use the reciprocity theorem. So are we done? Is it true that if I take the X to U flow, then the edge UV will contribute a good fraction of the energy? Not quite. Because it has to be relative. Right. So the potential difference is high enough, but there is a denominator. We normalize by the energy of the flow. There's basically one problem remaining. So we made sure that difference in potentials is at least, this difference in potential squared is at least a quarter of the UV difference squared. But the normalization is different. Here we're normalizing by the energy of the UV flow, whereas here we're normalizing by the energy of the XU flow. All right. So all that we need to ensure is that the distance from X to U in resistance metric is not too high, is comparable to the distance from U to V. Okay? And once we do that, we're done. So let me just put this together into the algorithm, and I think I need 5 minutes from here, and we'll really have the algorithm. All right, so here is the experiment. So to discover an edge UV with effective resistance, whose effective resistance is large, non-trivially large, here's what we're going to do. We're going to choose some vertex X that is not too far from in the resistance metric from U. Okay. So resistance is at most polylog. Then we will send flow from X to U and list all the heavy edges in that flow. And then we'll send flow from X to V, list all the heavy edges in that flow. By what we just said, the edge UV will be in one of the lists. Because remember, the thing that we needed from X, well, we needed two things. X is not too far from the endpoints of U and V. And the second part that we needed was that in the potential embedding of U and V, X should be, the experiment that succeeds is the one that corresponds to the further endpoint. So if we try both U and V, one of the experiments will succeed. All right, fantastic. So that's a nice experiment, but how do we turn it into an actual algorithm with a linear or nearly linear runtime complexity, we take the vertices of the graph and we want to partition them into clusters of bounded effective resistance diameter. Okay, so here's a pictorial representation of that. Then for every such cluster in the partition, we perform the following operation. We pick one representative vertex, x. Here's x. And we try these flow experiments from x to every other vertex in the cluster. So that's a linear number of experiments. For every vertex in the cluster, it's one experiment. By our analysis, any edge UV that is heavy and such that both endpoints are in the cluster will light up in one of the experiments and we will find it. So the only way that this approach fails is that our edge UV has the two endpoints in different clusters. And then it could somehow happen that the representative in U's cluster that we pick is somehow too close to U in the corresponding potential embedding, and the same for V. That would be a disaster. So we need to ensure one other property, which is that we don't cut heavy effective resistance edges. So why will this property be satisfied? Well, for that, I need to remind you what the resistive embedding is. The resistive embedding, I'm not sure Sushant covered that, but basically, the resistive embedding is a map that sends vertices of any graph into Euclidean space, and choose two-dimensional Euclidean space, such that the effective resistance between U and V is the square of the Euclidean distance between these vertices. So it's great that effective resistance is the square of a Euclidean metric. And now we can, equipped with this observation, we can state our final algorithm. We construct the resistive embedding. One can construct it after some dimensionality reduction. We use Johnson, Lind, and Strauss. Because it's a Euclidean metric, one can compress it very efficiently. Then we form this partition of the vertices using locality-sensitive hashing style techniques. We can just use locality-sensitive hashing. Now, this will have the property that an edge UV, such that U and V are close in Euclidean distance, will not be cut too often by the partition, randomized partition that results. And therefore, everything will be great. So in locality-sensitive hashing, there's this notion of a near distance, and we'll set it to 1, which is basically roughly the resistance that we're looking for. And so edges are seldom cut. A given edge is cut by a given partition with only 1/polylog probability. So this leads to a very efficient algorithm. Good. So let me pretty much end here, except I would like to mention a couple of open problems. So first, there's a very interesting open problem. The slow recovery primitive that I described to you before, the one that takes a quadratic number of tests, actually also extends to matrices. It takes more time to define this, but one can recover not just graphs, but spectral approximations to matrices this way. Our speedup, the fast method, does not extend to general matrices. We really use the structure of vertices. And it would be nice to find more applications on this. This I will not talk about. One very exciting direction that I would like to pursue is related to our previous discussion on dynamic versus sketching. Can one turn sketching algorithms into dynamic algorithms by basically saying the following? Here, I gave you an algorithm for maintaining a spectral sparsifier using an n-polylog n space, and I also showed you how to decode it in n time. Wouldn't it be nice to look at this sketch and directly prove, so to speak, stability bounds? In dynamic algorithms, one wants to always maintain an explicit solution. So what I could do is just at every step of the process, I could redecode my sketch. This, of course, would take n time per step, and that's not very nice. But on the other hand, how different are the sketches across for neighboring graphs? That seems like a very interesting question. Just prove that sketches are stable, and the outputs of the sketches are also stable. If that is successfully done, then we'll have a nice hammer for turning low-space sketching algorithms into dynamic algorithms. Would be fantastic. All right, thanks for your attention.
Thank you. Questions?
So did you do that for the last problem? The last thing you talked about? Did you try to make it into a dynamic algorithm?
I tried, not very, very hard. I couldn't, but I think one should try harder. So there's some very interesting questions, even basic questions that arise here. For instance, I mentioned that in order to do the decoding, we need to explicitly maintain the resistive embedding, right? And basically, you should just know what the resistances between vertices are, right? This resistive embedding is an embedding of vertices into log n dimensional or so space, right? Basic question, can one maintain this embedding? One edge in the graph changes. So suppose you had a JL'd version of the resistive embedding, then one edge in the graph changes. Can you quickly see what's going on there?
Under deletions, that sounds really intense.
So forgive my ignorance, is this known for spanning trees that you could use n polylog n space in insertion deletion stream and maintain polylog for update amortized? Or is this just open?
For minimum spanning tree, worst case time? No, not worst case time.
No, but
amortized,
sure.
but n space.
exactly, so it's
but
known.
n polylog n space.
Oh,
Because I guess in
But that's exactly
principle,
what we
you could
discussed,
use the sketch in every round. That would be n polylog n space. So in principle, this is doable. It's just not clear how it interacts with runtime, if I followed correctly.
Right. No, but Valerie, this is not exactly what we discussed. So your paper on the archives.
that was a minimum spanning tree.
Oh, not minimum. No,
Just any spanning tree.
No, just
Spanning
any.
tree
Right,
is
not
the way,
minimum.
yeah.
Yes. So the answer is yes. So
Cool.
for the first
Thank
part
you.
of this talk, the answer is yes.
Yeah.
It's on the archive.
Okay, thank you.
But it isn't hard to do.
Yeah. It's not hard.
Gotcha.
Valerie says.
No, it's just comes out.
I see. So to clarify, the open question is something analogous for spectral sparsifiers.
Right. Or an
That is-
easy-
that is
yeah.
open.
Exactly. Or an
I mean,
easier question
I don't know.
for cut sparsifiers.
I see.
Let's say for spectral sparsifiers, one needs to mess with
Fair.
resistances and maintain Laplaces, system solvers under deletions, and I think Richard Beng has some
You know,
papers on that.
But this stuff, you could spend time for querying, right? You don't have, in dynamic algorithms, you don't have to have like an explicit representation.
Mhm.
So
No, I didn't understand actually.
you could spend time to answer a query, like you don't have to do it in O1. It doesn't have to be you look it up.
Right.
It's explicitly there. You
Yeah.
could compute something that would give you the query if you could do it quickly, that would answer a query.
Oh, what's a query actually?
Well, when things change and you want to know, you might have some representation which will, well, you have to define what a query would be in this case.
Oh, a query to you is delete an edge or add an
No,
edge.
that would be an update. A query
That's an
would
update.
be, I don't know, is this edge in, some question that you're using the data.
Is this edge in the sparsifier?
Yeah,
You're saying like you could ask for the query not return, like needing to maintain an entire spanning tree, but answering connectivity or like presence of an edge in the current tree or
yeah. Or is this edge in the minimum spanning tree? Maybe you don't have the exact list of edges. Maybe you just ask, you process it, and it takes log n time to figure it out, or log squared n time to figure it out, right?
Yeah, that could be nice. Right?
Yeah.
This could be some an intermediate version of something that's hard.
Then we really also have to worry. Then we also have to worry about this adaptivity or oblivious adversary, because if the query can ask which edges are there, then you're going to be screwed very quickly.
For now, I want a problem that is oblivious.
Okay.
Right? Because making sketches adaptive is a whole new thing, right? But I find it very compelling to just say oblivious adversary. Right? But just maintain the solution in small space and also explicitly on the side.
any more questions?
Hey, did you answer Chandra's question?
Yeah, I'm back.
Yeah. So forget spectral for cut sparsifiers. Maybe it's easier the answer to sort of. So what do you make? I mean, I guess how do you do this? Sort of use some recursion to
Let me do it for spectral because it's very beautiful and it's quick. So basically, it's a beautiful idea from Miller and Teng, a paper called, I think, on the addition and removal of artificial bases. So as I said, right, we have a sketch of our graph, and then we want to have a crude sparsifier of our graph, like a factor 5 sparsifier, 10 on the side explicitly. How do we achieve this? Now, we don't just go and sparsify G straight away. We consider a sequence of graphs. take G and regularize it. Add a lambda times complete graph to it, where lambda is a parameter. So for example, when lambda is 1, then then the complete graph is a good approximation to this graph. So you have your crude sparsifier already. So you can sparsify this graph by having a sparsifier of the complete graph in hand, which you do. Right. So then you consider G plus lambda by 2 times the complete graph. Once you have sparsified this, now this is a factor 2 or 3, 2 times 1 plus epsilon, spectral approximation to this. So you first decode this guy, then you sparsify this. Once you have an explicit sparsifier of this, you consider lambda by 4. And once you get to lambda by n squared or something of this nature, it's pretty much G. So everything's good. Yeah, it's a very, very cool idea. I think it's also called the homotopy method, right?
All right, let's give a big round of applause and thank you for the full suite of lectures today. Thank you very, very much. That's it for the schedule today. We'll be back as usual tomorrow at 9 a.m. For coffee, and the talks will be at 9:30 on optimization. So, see you all tomorrow.